Get started. I'm Charlie Smith, the Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, or the G-PST, whose mission is to bring together key actors from across the globe to catalyze a rapid clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. The foundation of the G-PST is a group of 6 system operators from around the globe who are facing higher penetrations of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium are research and peer learning, technical support, workforce development, technology adoption support and standards, and open data and tools. ESIG is the lead on Pillar 1, and more information on the G-PST can be found at globalpst.org. As the lead on Pillar 1, ESIG would like to welcome you to the February monthly webinar of our joint G-PST Pillar 1 ESIG webinar series. This series is an addition to the regular ESIG monthly webinar series and focuses on the G-PST research agenda and associated topics being addressed in Pillar 1. Topics are presented by both the founding system operators and other advanced system operators active in Pillar 1, as well as members of industry and the research community participating in the activities of the Research Agenda Group and the Research Advisory Committee of Pillar 1. An additional series of webinars on the other 4 pillars of the G-PST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about G-PST and how to engage, please go to globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I'd like to go over a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we use the Slido platform at slido.com. You need to open a browser window, go to slido.com, and enter ESIG21 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save about 10 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Okay, today's topic will be on developing an understanding of grid forming, or GFM, inverter specs. This topic is an integral piece of the Unify project, which is co-led by NREL, EPRI, and the University of Washington, and funded by the Solar Energy Technology Office at DOE at the level of $25 million over 5 years. The Unify project is focused on the research questions having to do with grid-forming inverters, and the topic of grid-forming inverter specifications is an integral part of the discussion. It's taking on increased importance as we move closer to the commercial deployment of grid-forming technology. And here to tell us about it is Ben Kroposki, the director of the Power Systems Engineering Center at NREL. You may recall that Ben was with us about a year ago to tell us about the overall Unify project. We're very fortunate to have Ben here with us today. Ben is both a professional colleague and a good friend. We've worked together on renewable integration activities for the last 15 years, both of us serving as guest editors for different renewable integration issues of the IEEE P&E magazine during much of that time. Ben has nearly 30 years of experience in dealing with the integration of renewables in the planning, design, and operation of power systems, and is an internationally recognized expert in this area. Ben currently serves as the organizational director of the Unify project as well. And just as a note of interest, we have 151 common connections on LinkedIn, working with many of the same people over the years. I consider Ben a good friend and a good friend of ESIG, and it's a pleasure working with him. Today's webinar will discuss the development of specifications and requirements for grid-forming inverter-based resources that have been developed by the Unify Consortium. As synchronous generators from traditional fossil fuel plants are removed from the grid, The power system will be increasingly reliant on grid-forming IBRs to maintain stable and reliable operations. I greatly value Ben's contributions to e-cig and the industry, and I look forward to what he has to say. Okay, just a short reminder once again to use Slido at slido.com with the event code of e-cig21 to ask your questions. And without any further ado, let's go ahead and get started. Ben, I'll now turn it over to you.
Okay, thank you very much, Charlie. I'm going to go ahead and share my slides. And we'll go ahead and get started. So today I'm going to talk about understanding grid forming inverter specifications and what we've been working on over the last year in the Unify Consortium. But first, let me talk a little bit about the need for grid forming inverters and really why we're putting so much effort into this space. So last year, NREL put out a big report that really looked at how to get to 100% clean electricity in the United States by 2035. You can see the link right there, as well as you can see the title of the report and go dive into it a little bit more. But I wanted to pull out one specific piece of this report, which is the fact that wind and solar are going to have to become one of the dominant providers of energy to reach this 100% clean electricity target. And inside this report, it basically says that you're going to need something on the order of 60 to 80% of the total energy for the electricity system being provided by these variable renewable technologies. That is roughly around 2 terawatts of wind and solar deployed into the grid, which is a long ways from where we are today. But as we progress over the next 15 years, we really want to make sure that we have an electric power system that's capable of allowing this much wind and solar to be integrated. And I'm going to focus in on explaining some key technical challenges to address these kind of levels and what we're doing about it. Now, this slide right here is kind of a summary slide of what do we know today about operating power grids with high amounts of wind and solar. And you could use the percent wind and solar here as a proxy for inverter-based resources, or IBR. And as you look from the very small system sizes, things that are like small island power grids, you can see that we know today how to operate those with relatively high levels of wind and solar. And if you look at these red boxes, what that is telling us the instantaneous level of inverter-based resource at any particular point in time. And the gray circles are telling us the annual percentage levels. Now, if we take a look at this, you can see as we go from small island power grids that we operate at fairly high levels to larger island grid systems, all the way up to larger grids, we kind of get this curve if we look at the instantaneous level of inverter-based resources. So some of the Hawaiian Islands are actually operating at very high levels of inverters today, and even larger grids like Ireland is up to 75%, all the way coming down to, if you included all 3 interconnections of the United States, we're actually instantaneously, like on an hour-by-hour basis, around 30% wind and solar reduction. That translates, as you can see, to these gray circles. So going from 100% on an annual basis down to around 13, 14% where we are today across the continental United States. The nice part is we've seen these numbers actually increase dramatically over the last couple of years. So a few years ago, this curve looked like this. Now we've migrated to this curve here, but what we really need to be able to do is get this instantaneous curve up to this level. So it has to basically be operating close to 90 to 100% instantaneous levels if we are going to get these annual averages up over 50% and closer to the 60 to 80% that we need across the continental United States. So we have quite a ways to go from around 14% up to something around 70%. But we can look back here and we see that, on these smaller scale systems, we're making a lot of progress. A lot of these are adding more and more inverter-based resources, and especially the smaller ones are adding the grid forming technologies. So I'll get into specifically where we are with grid forming and why we need grid forming technologies. Another way to think about the power system and what I just showed you there was instantaneous penetration levels of inverter-based resources, where you just divide the total amount of inverter-based resource divided by the total generation. That gives you that instantaneous level. The challenge with this number is it isn't very exact, and it doesn't tell you things like grid forming capability. So we've been looking at a variety of different ways of evaluating this, moving on from a single number to maybe something that looks like an inertia constant. And the inertia constant basically is just taking a division of the amount of synchronous machines and rotational mass that you have on the grid and divide that by the total generation that you have on the system. Again, as we look toward grid forming inverter capabilities, you don't see that really accounted for in these types of equations. So I would like to point out a couple of people are thinking about this. This is from a recent article from Andy Hoke and Fahan Gevorgian at NREL, looking at voltage forming ratio and how to actually add in voltage forming inverter-based capability into these kind of calculations to account for that added capability from these type of technologies. Again, as we kind of go work our way through this challenge of integrating more inverter-based resources, we want to make sure that we're able to account for different capabilities that these inverter-based resources have. Another question that's worth asking and thinking about is, when do we actually need grid forming technologies in the system, and how much do we need? So I wanted to point out some recent work from a couple groups. First off is a group associated with the UNIFI Consortium, where they took a look at an IEEE 39 bus test system. So for people that are familiar with doing studies on power grids, this is a very well-known test system. It's got several generators scattered throughout a large integrated transmission system. And what they did was take a look at this and replace the various generators on here with either synchronous machines or grid following inverters or grid forming inverters with either droop control or virtual oscillator control. This graph up on the top is basically showing that they ran roughly 250 cases and deploying a variety of different technologies. The key thing here, as you can see in the coloring, is it's a very big mix of generators and inverters all scattered at different buses and at different levels. The key piece that this shows you is the fact that these grid forming inverter controls, virtual oscillator control or the droop control, all the cases were stable when they looked at those technology deployment. Whereas on grid following, roughly about half the cases were unstable. And so let's take a closer look at those unstable cases and where they were appearing in the system. So if you take again that particular one, the 39 bus IEEE system, and you look at this graph here, this is showing you penetration levels of grid following inverters. From 0 to 80%, and then the percentages of cases that are stable. You can see basically there's a line here that's going down, and as you would expect, as you had less of these grid following inverters, you had a more stable system. As you increase the grid following levels, you had a less stable system. Of course, there's some little pieces here that go outside that just nominal straight line. And if we take a closer look at what's causing these particular systems, you end up finding that those are mostly caused by the fact that your buses that are furthest away from the rest of the generation sources, in this case bus 38 or generator 9, actually had the least number of stable cases. So what this ends up showing you is that in general, you get this decline in stability if you're only using grid following inverters. And there's a tipping point where your systems become more and more unstable. It is also heavily dependent on where you actually place your inverters, and the further that they're out on the system or the weaker the grid that they're interconnected to, you're going to have more stability challenges. So these, answering the question of when do we need grid forming and how much do we need, it's very dependent on the system characteristics. This is a test system, but you could do this kind of characterization with any realistic system. It's also highly dependent on the types of disturbances and also the nominal voltage and frequency ranges that you want to keep your system into. Stability issues increase as you put more and more grid following inverters on here, especially once you get above 60% instantaneously. And the systems are going to have corner cases. Even at very low penetration levels, there's still some amount of cases that are unstable. Now, that's especially true when you start to move these grid following inverters and highly concentrate them in weak parts of the system. But grid forming inverters, on the other hand, they actually were able to make all cases stable and really are going to play an important role as we look to maintain overall grid stability in large-scale deployments. And if you take a look at those, if you remember from the graph I showed a couple of slides ago, the Hawaiian systems right now are pushing these limits, and we're looking at how we can put grid forming technologies into those so that we can get up to 100% instantaneous levels of inverter-based grids. Now, in addition to that study, I wanted to show a different study. You can see the reference there at the bottom. This is a great paper that showed a lot of different examples, but one that I pulled out of here took a look at the Australian system. So this is the NEM in Australia, and then it mapped over here to the one-line diagram. They did a similar thing where they went and deployed a lot of inverter-based resources at different penetration levels. And interestingly enough, basically came to the similar conclusions. Basically, above 60 to 70%, they started seeing much more stability issues. Grid forming technologies can actually help stabilize some of these particular issues. And again, the location of where the grid following inverters were being deployed actually was a significant contributor to the stability of the overall system, and that grid forming inverters should be placed at weak points in the grid. So there's some basic general rules that are starting to get developed now that we've been taking a look at these types of systems for a couple of years. In general, the 60 to 70% is a level, and again, that's instantaneously, which we're going to be reaching very quickly. You can get to those levels even with 30% renewable deployments on an annual basis. And how you actually deploy these in your system, making sure to strengthen the weak places in your grids with grid forming inverters will be critical moving forward. So there are a variety of technical challenges with adding in higher levels of inverter-based resources. We talked about the stability challenge basically on the last couple of slides. What that means is that once you have a disturbance in your grid, how fast can you recognize you have that disturbance and, for example, bring a frequency back into normal operating conditions? We've shown many times that even with grid following inverters with advanced controls, you can improve the frequency response to those types of systems. But with grid forming inverters, we've shown that you can get an even quicker response and actually help maintain operational stability. There are still serious issues around protection systems and how to deal with the fact that you are eliminating large short circuit currents, which your protection system in your grid may be made of. There are lots of opportunities, whether you're looking at things like adding synchronous condensers into your system to provide that fault current if you want to maintain the existing protection system, or looking at having inverters provide slightly more than rated level current. Grid forming in black start is going to be increasingly important, just making sure that we have inverter-based resources that are capable of restarting the system from a blackout condition and providing system restoration, and are integrated with whatever type of system restoration processes we have for the grid. And there's a lot of specific details on what you need to take into account when you're looking at having your inverter-based resources provide that capability. And then as we start to deploy more and more of these inverter-based resources, the control algorithms inside them potentially can be causing oscillations as they are reacting to disturbances on the grid. And we want to make sure that we're building in functions inside the control algorithms that can dampen some of these system-wide oscillations that may be occurring. So again, a variety of these technical challenges with inverter-based resources. Now, historically, everything that we've been building with large-scale bulk power integrated inverter-based resources have been using a grid following capability that basically is controlling the output current, and it's completely dependent on another device like a synchronous generator to develop that voltage waveform in order to synchronize to. And we would think of these as followers in the system. And then what we've been working on is these grid forming controls, which are actually controlling the voltage waveform. It can make its own waveform without another synchronous device, but it can also synchronize to existing devices that are providing the AC waveform for the grid. But again, depending on the conditions it has, it can be a leader for the system and operate the grid from there. There's a variety of benefits for using these grid forming inverter technologies, including maintaining the system voltage, having extremely fast responses to disturbances, the black start capability. And as I kind of mentioned here, these are going to be key technologies for enabling higher levels of wind and solar. So above 60 to 70% instantaneous, you really need to be evaluating grid forming inverter technologies and how those can be deployed in your system. They can improve the system reliability and resilience, as well as providing economic value from providing a range of grid services. So as we migrate to this world where we'll be needing grid forming technologies, we've been looking at a variety of specifications. So people have been developing these types of specs for the last couple of years in Australia, in Europe, in the UK, in the United States, kind of trying to get some consensus around what we need for these type of inverters. The challenge is this is kind of the Wild West right now in terms of all sorts of different specifications being proposed. What we're looking to do is figure out a way, how do we bring consensus around this so that we can have standard products developed no matter where they are in the world. The vendors can build a same type of product, and the system operators and utilities can make sure that they are being, the systems that are being integrated can operate in a proper way. So in the past, if we think back to the very beginning of the power industry as a whole, back in the 1880s and early 1900s, this was a challenge that people had with synchronous generators. But we've spent a lot of time in the early versions of what became IEEE and the societies around electrical engineering developing these interoperability guidelines for synchronous generators. We need to do the same thing with grid forming inverter-based resources. So in the US, we've been focused on developing a new consortium called the UNIFI Consortium, which stands for Universal Interoperability for Grid Forming Inverters. This consortium really is this forum to address the fundamental challenges of seamlessly integrating grid forming technologies, of inverter-based resources, and unifying them with the synchronous generators that exist today. And the key there is you have to unify this, because you will have all sorts of different power systems operating with different levels of inverter-based resources and synchronous machines. So we kicked this off in January of last year with the Department of Energy funding from the Solar Energy Technology Office and the Wind Energy Technology Office. We currently have 22 industrial participants that span the range of the inverter vendors and manufacturers, utilities, system operators, and system integrators. 5 research labs and 12 universities all working to solve this challenge. And if you think about what the challenge really kind of revolves around, it's how do you specify grid forming technologies such that the grid is making sure that you're providing reliable, stable operations from the grid's perspective. And then from the inverter perspective, how are you actually defining those interoperable requirements and interconnection requirements in a vendor agnostic way? So how do you keep the grid operator happy? How do you keep the inverter manufacturer happy with their proprietary controls? And how do you map these together? So we've been exploring a number of different ways of how do we develop specifications around this particular area so that we can have controllability and interoperability across multiple vendors. So over the last year, we've gotten together several times and started to try to develop sort of some universal principles or rules for implementing this into the future. So we wanted to come up with a set of sort of universal principles that really were forward-looking and understanding how do we make grid forming inverters map to the power system now and work better into the power system of the future. We spent a lot of time working on terminology, including just what is a grid forming inverter and how is that defined, developing use cases, so all the way from small microgrids to distribution systems to bulk power system integration, and then figuring out how would we validate these rules and requirements, and if we needed to make improvements, pass those back and create this feedback loop that is developing in a relatively fast fashion the specifications for these technologies. So if we take a look at the universal objectives, we wanted to first agree, what do we think these things need to do? We wanted to make sure that they supported seamless transition between grid connected and islanded mode. We wanted to recognize that on AC power grids, you use system frequency as this universal power sharing parameter. You wanted to make sure that we realized appropriate inertial and damping constants that are built into how the grid operates today. We wanted to make sure that they responded in proper ways to severe transients and faults, that they maintain system balancing and stability, support the ability to be connected or disconnected, support the ability to trip if necessary, use cyber-secure communications, including a variety of techniques, including black start from those, be able to be dispatched and use droop, which is kind of how the system operates today, and then look at how to support interconnection grids and fault current injection and provide good power quality. So those are kind of universal things that we thought we should be able to accomplish with these specifications. Next is how you take this, nice list of 11 things and map that over into a specifications document. So this was just published in December of last year, which was our version 1. Note, obviously, it says version 1 because we intend to keep updating this document. And if you want a quick link, you can scan this QR code over here. But this gives you an idea of what is inside that document. And it's publicly available right now so that you can take a look at it and start providing feedback to the working groups on how to update this particular document. But it's designed really to provide these functional requirements for integrating grid forming technologies into power systems and provide uniform requirements for any type of inverter-based resource. This slide kind of shows you where we were with that initial set of universal objectives and how we then map that over to the specifications section. I won't go into this in too much detail, but I'll start walking through the document a little bit at a high level to give you an idea of what's inside this particular document and how we're using these specifications. So first thing is the scope. We want to make sure that this is inclusive of any grid forming inverter-based resources that connect to larger scale systems. So this should be able to be used for microgrids, distribution level, transmission scale equipment. and covers a full range of grid forming technologies, whether it's PV inverters, wind turbine inverters, even HVDC. These things all have some device in there that could be potentially a grid forming technology. And the purpose is to provide these uniform specifications so that you can integrate these easily into the systems. Now, we split up both a set of universal performance requirements that every grid forming inverter should have and some what we might call grid forming plus. We'll get into those in a second, but first let's cover sort of universal performance requirements. And we want to understand what they can do under both normal grid operating conditions and abnormal grid operating conditions. So first off, operating under normal conditions. So we want to make sure that these grid forming inverters autonomously support the grid. Now, this is also a capability that you'll see in grid following inverters, but we wanted to make sure that people realized that both of these technologies can do autonomous support, meaning they're going to locally measure voltage and current, and they're going to be injecting power or maintaining voltage depending on what type of setup they have autonomously without any type of commands. We also want a dispatchability of power output. So this is something that we're seeing now more often, is this ability to send a command out to these devices so that you can dispatch power up or down, for example, curtailing solar or wind when you have too much of that on the system. But this is going to be more of a dispatch command. Again, grid following inverters should be starting to have this capability, but grid forming ones also. In addition, we want to look at things like providing positive damping to voltage and frequency oscillations. I'll put a plug right in here for our Unify seminar series, which we also do on a very regular basis in the spring and fall. But this graph right here is from one of the recent talks from the Kauai Island Utility Cooperative. There's a place right now where we have a lot, extremely high level of inverter-based resources, and probably one of the few places in the world that today is operating grid forming inverter-based resources on their system. But one of the key things that we want to make sure is that as we add these inverters into the system, they have some type of damping once they start to see oscillations in the grid. And one of the challenges we have right now is not necessarily understanding what all those possible oscillations would be. So we need to make sure that we're starting to build in that sort of a damping coefficient, if you will, against oscillatory behavior on the grid. We also want these devices to do real and reactive power sharing across a variety of generation sources. So when they're all working together, they can share the power load from the system. And then a couple more things under normal operating conditions. We want them to have very robust operations under low system strength or a weak grid. And people may not be that familiar with that term. I threw in a little bit of information over here on the side from the Australian system operator, AEMO, where they actually kind of publish what they mean when they're talking about system strength. But in general, what that refers to is when you have changes in the system, how the other devices react to that. Usually on a strong system, you don't have very big reactions to disturbances. And on a weak grid, you can potentially have very large reactions in voltage and frequency. And so you need to make sure that your systems are able to take that into account. And then, for example, we also want to make sure, at least on three-phase systems, that there's an ability to do voltage balancing on those systems. Okay, so as we look away from normal to abnormal conditions, so fault type conditions, we want to ensure that these technologies have proper ride-through behavior. So examples of that you can see over here in this particular figure. If you're at 60 hertz and you experience some type of event, then if you have too far of a frequency fall, you may dip below an under frequency load shedding threshold that may start to drop load. What we're able to do with very fast grid forming and even some of the grid following inverters is actually arrest that behavior by injecting power and create a more stable situation. I'll put another plug in here if you're interested in much more detail on grid forming technologies. There's a great EPRI grid forming inverter tutorial that we have linked through our Unify website that you can find out a lot more information about. But in general, we want to make sure that they have proper ride-through behavior, proper response to asymmetrical faults, and also response to abnormal frequencies. And then continuing with this operation outside of normal conditions, you may have things like response to phase jumps and voltage steps that you would see on the grid. We want to make sure these grid forming inverters have the ability to either absorb or inject active and reactive power to resist those changes that are happening very quickly on the grid. And then finally, intentional islanding. When we go to a microgrid type mode and we disconnect from the rest of the grid, that they're able to maintain stable voltage and frequency inside that island system. So you may have a small customer-sided microgrid or a much larger microgrid, depending on your setup. If you have enough grid-forming inverter technologies in there, we want them to make sure they maintain stable operations in those microgrids. There's an additional set of grid forming capabilities and considerations, things like black start, regulating voltage harmonics, the communications between system operators and the plants, voltage and frequency signal response, and short circuit ratings. These are all things that we need to think about for additional capabilities beyond just the universal specifications. So I'll mention these relatively quickly here. Black start. Now that could be considered maybe a grid forming plus service. We know that they can create their own voltage waveform, but do they really have the capability to do complete black starts? That's a different question, because now you're adding in the ability to restart transformers from a coal or re-energize lines. And these things are important to take care of in terms of the capability of the sources that you may have in there. So there's information around how best to start using grid forming technologies for black start capability. Another thing is things like communications and secondary response. When a grid operator is passing signals down to all of these distributed devices and technologies, how do we make sure that they're doing so in a cyber secure manner? How do we make sure they're passing the secondary type control signals that are being used for mostly power adjustments in the grid? And then things like short-term rated current. How much output current can you get from these inverter-based technologies is going to definitely be dependent on how they were designed. I'll just say that, what we want to be able to do is specify what this short-term rated current is going to look like. Maybe it would be 1.5 times full rated current for 2 seconds. But inverters are going to have some amount of controllability in this aspect, and you may want them to have a lot of short circuit current or not a lot of fault current. And really that has to be designed into the system and discussed with how they're operated with the rest of the protection grid. The other constraint that you may have with grid forming technologies is what's on the DC side or the input source. So it could be things like a wind turbine, you could have a PV system, you could have a battery. Each of these is going to have sort of different response characteristics on the DC side of these inverters that may give you a difference in how they are performing overall in the context of the system. So how are we taking all these requirements and doing some things inside our Unify Consortium to address these and validate that they're actually working? So first off, we want to make sure that we're developing models for the grid forming technologies. So we have a working group that's working on modeling and simulation, building grid forming inverter plant models, and then wanting to figure out ways to with just the plant modeling capability to look at evaluations of things like voltage step or frequency step and which specifications they can verify inside of that system. So we're working our way through a variety of test network use cases to verify that as these specifications get developed, there's a set of modeling and simulation technologies and programs available to verify that output. Some quick little preliminary results, right? We wanted to do a step change in voltage, and then we're looking at various types of grid forming technologies, whether it's droop or whether it's virtual synchronous machine or whether you have a grid following plant, and evaluate what the response characteristics look like to step changes in voltage and step changes in frequency. Again, with the idea that we'd be able to validate some of those specifications in just the modeling and simulation area. Now, to go beyond that, we're starting to put together several actual hardware experiments. Our first one is a multi-vendor experiment at the 1 megawatt level, where we'll be able to set up individual inverter testing, evaluate their grid forming capabilities, but more importantly, look at multiples of different vendors, all trying to meet those specifications and verifying that these multi-vendor grid forming technologies can actually work together across a variety of scenarios. So both at this scale, at the 1 megawatt scale, where we're interested in understanding how this mix of technologies work together. So whether it's single phase technologies, three-phase technologies, whether we're evaluating grid forming inverters or grid following inverters or synchronous generators, a variety of actual real world hardware connections to validate that these requirements will, at the end of the day, give you a working system. And then we want to go bigger than that. We are looking at 20 megawatt plus demonstrations of grid forming technologies. And this is where we're going to have inverter-based resources that are going up to this really utility scale. The one reason I'll point this out here is that if you are listening to this webinar and would have some place where you are thinking about putting grid forming inverter technologies at over 20 megawatts, we'd be very interested in following up with you. What we've been able to do right now is work with a variety of our partners as part of the Unify project to identify the benefits of using this grid forming technologies, ensure that the interoperability of these will be compliant with the variety of standards, formulate a test plan, for example, commissioning tests for looking at these large scale systems, and also evaluate the field performance. And we want to make sure that we're able to really understand a variety of technologies. So whether it's the renewable technologies like wind and solar, or energy storage technologies, or some combination of all of these, we want to make sure that multiple vendors can work together by meeting the requirements that go into the specifications document. So we want to look at how well we can do real and reactive power dispatch. How well do the things respond to voltage and frequency droops? How do we do this power sharing amongst all these different devices? Additional capabilities would be to look at black start capability to maximize system resilience and improve the overall stability of the grid at high levels of inverter-based resource deployment. So again, we're really interested in looking at these larger scale deployments, and we have a couple that we're investigating right now, but we're looking for more examples, especially in the United States, where people are considering these large scale grid forming inverter technologies. So just to kind of summarize everything, and again, if you want to visit our website, you can get the public version of these specifications and start looking at them. But we know that wind, solar, photovoltaics, and batteries right now enjoy favorable economics and are starting to be deployed at a high rate. All these technologies are inverter-based resources. The challenge is that most of these are all grid following inverter-based resources. So IBRs are soon going to be a dominant part of the power grid many hours of the day, either during windy times or during the middle of the day when there's lots of sun. IBRs are going to be a significant portion of the grid. And we need to ensure that these inverter-based resources and synchronous generators work together in a unified approach to ensure stable and reliable grid operation. As I showed you earlier, grid forming inverters are needed to provide grid support and stable operation above 60 to 70% instantaneous levels, which translates to maybe 25 to 30% on an annual basis. And there are lots of power grids in the United States today that are starting to reach those levels. So we've been working on grid forming specifications, models, testing procedures, and integrated processes. All of these are needed to make sure that we address these issues. And the Unify Consortium is actively working on all these items and more. We're also looking at education and workforce development of how to take these lessons learned from these systems and make them broadly available to the industry. So with that, I want to thank everyone for listening today, and I also want to give special thanks to the Unify Consortium area leads. You can see them listed there, but they have been a great help at putting together all the information you've seen in the consortium to date. And I also want to thank all of our industry members that are part of the Unify Consortium. So thank you.
And thank you, Ben. That was a nice little walk through what's going on with the specs and the grid forming in the Unify project. And it's stimulated a lot of questions. In fact, we're over 50 questions now. We're not going to be able to get through them all, obviously, but as we mentioned at the beginning, Ben has graciously offered to follow up on the questions we don't get to with some short answers, which will be distributed to everyone. So let's dig in here. What are the obstacles to installing grid forming inverters? It seems like it's obvious to do so. So why wouldn't 100% be grid forming going forward?
Yes, on the surface, that's the case. The challenge that you have today is that it's not what all of the vendors have available, number one. Although most of the inverter vendors can build a grid forming inverter technology, they're not being requested to provide that technology. So as one of our good friends, Julia, says, it's the chicken and the egg problem, right? You have a technology that can do something great, but you don't necessarily have it either being required or asked for, and then people don't know exactly what to require or ask for. So that is where these specifications that I discussed here today is trying to solve that particular challenge. This gives utilities a way to ask for these grid forming technologies, and it also gives a way for vendors to make sure that they're building something that's going to be compliant with them. The bigger challenge we have today is the fact that all of these things aren't completely sorted out. So we do need to do this in relatively quick terms, and why we're working with the industry right now to get these specifications designed, built, verified, so that in the future, this will just be normal. People will all just get grid forming inverters and they'll work properly with their system, but we're not quite there yet.
Yeah. Ben mentioned a couple of things there, but Julia Matoiva-san is working with e-cig on this through our reliability working group, along with Jason McDowell from GE, who's working with e-cig for a couple of years as well. There's a lot of activity going on in this breaking the chicken and egg cycle, and that work is also feeding into the G-PST Pillar 1 activities that I mentioned at the very beginning. So very good question. A lot of stuff going on, a lot of collaboration with NREL and e-cig and EPRI and G-PST and vendors and consultants. So stay tuned on that. It's a lot to keep up with. Next question is from Colton, and if I had to guess, I would guess that's Colton Ching, our good friend from HECO. Are GFM IBRs able to address system strength issues such as short circuit ratios and adequate fault current for high IBR scenarios?
Hi, Colton, and thank you for the question. Yes, so that particular question, they're definitely able, right, to address stability issues. I kind of covered that. On the protection side, the challenge that we have, I think, with inverter-based resources is historically they're not designed to provide an extremely large amount of fault current. So just the design of synchronous generators, when you fault them, they typically can give you 6 to 8 times the amount of normal rated current as fault current for an extremely short amount of time. And that is often used in protection schemes that are dependent on overcurrent. So the protective relays or circuit breakers or fuses recognize that fault current is happening, and they can actually open up and disconnect that device. Inverters, on the other hand, um, they're not historically designed to provide that amount of fault current. If you wanted them to provide that amount of fault current, you would have to over-design several components in that system, and that would, of course, drive up some of the costs. That being said, you may be able to get away with having the inverters provide 1.5 or 2 times fault current instead of 6 times fault current. Is that enough for the protection system? You probably are going to have to retake a look at your protective relaying to see if that is adequate for identifying fault conditions. Um, there are other ways of addressing the lack of fault current from inverters, including adding synchronous condensers into your grid or repurposing some of your synchronous generators. I think the biggest challenge we have is the fact that grids of the future are going to be transitioning from inverter dominated to synchronous generator dominated and back and forth probably for the next decade or two, maybe into the foreseeable future. So addressing all of those issues around short circuit is going to be a challenge for a high inverter-based grid, and we're going to have to come up with some devices in there that provide that short circuit current if we want to keep the existing protection system. If we want to redo a protection system, we may have different options to address that challenge.
Good topic for another webinar.
Yep.
Next question, it keeps popping up here about the slides and the recordings. The answer is yes, the slides and recording from the webinar will be available, and you'll be notified in one of the subsequent follow-up emails. Question on system stability again, Ben. How sensitive is system stability to the particular control gains and control sampling rates implemented in the various GFM inverters on the system?
That's an
Haven't
interesting
done enough
question.
simulations yet, huh?
Yeah, we've definitely run a number of simulations, both NREL and a variety of our partners in the Unify Consortium, and are looking at that. I don't know if I have something that specifically tells you the sensitivities of all those parameters. I'll answer it this way. The challenge you have is there are actually a number of parameters that you can then start to program into inverters, and even more parameters than you have on a synchronous generator. There you're usually dictated by the physical design of the machines themselves, somewhat on the control, higher level control algorithms, but on inverters, they're fully programmable. You can set all sorts of gains on any of your control loops. And some of the challenges we've seen in the past is how fast these control loops are operating. There is a lot of sensitivity around there. We do have one of our working groups inside Unify that is working on control algorithms, and probably that particular topic of where do you start to set your gains on the variety of control algorithms and parameters that are being used is a whole nother webinar or topic. But what we're trying to do is come up with some general specifications so that moving forward, people have a good idea of what are appropriate values for some of the basic settings inside these different control algorithms. Even inside grid forming, there's at least 3, if not more, 5 plus types of grid forming algorithms that are out there and published. They all have different types of settings that are important to understand how they work in order to maintain stable operations.
Okay. Another one on controls. In a PV plant, how does the grid forming control interact with the maximum power point tracking algorithm that has already been developed by the vendors?
Yeah, well, the maximum power point tracking algorithm is, well, it depends which type you have. Again, depends what type of max power point tracking algorithm you've deployed in your system, but that's really, obviously changing the DC input side control. Whereas a lot of the functionality that we're talking about is the AC output side. It is, you are going to have a little bit of changes there if you're using your AC output to impact your maximum power point tracking control. But I don't think you're going to get way off your maximum power point curves. Of course, that being said, if you start to do things like curtail or other things, those are going to all impact the MPPT algorithms that you've deployed in your system. There are a variety of other additional control algorithms besides the PowerPoint maximum PowerPoint tracking, how you do your under and over voltage and frequency uh, um, ride-through settings. Now realize those ride-through settings, you're talking about 2 seconds or less. Maximum power point tracking is probably slower than that, I would suspect, because you have to deal with clouds and other things. So that's probably a little bit slower time scale than what we're talking about with response to grid faults.
Okay. Um, Dynamic models. You have any idea, will there be a standardization effort on the development of generic dynamic models for grid forming to be included in the specs?
Well, we are including them in the specs, I don't know, but we are working on generic grid forming models for the variety of software packages that are out there and available. We're trying to work with the various vendors from the inverters and with the software vendors to develop more or less generic grid forming models. Will that be in the specifications? I think that is to be determined. What parameters and what information actually need to be in a specification, though.
It sounds like something that may be more an interconnection requirement than a spec, but I guess we'll see how that develops. There's plenty of precedent for that to build on, though.
Right.
So what kind of software studies are to be used to assess these issues? Power flow, stability, EMT, fault analysis,
All the above.
all of the
So
above.
our modeling and simulation group is looking at everything, all of those things. So positive sequence load flow type models, steady state conditions, transient conditions, EMT models for these devices, as well as fault models. So we're looking at that full range. You're going to need all of those different types of models to understand the impact of these devices in your power system.
Okay, here's a very detailed question, Ben. If you need to, save it for the written responses, that's fine. But to use grid forming inverters, they must be reliable with grid phase jumps. What are your proposed maximum phase jump values for grid forming inverters?
Yeah, right. That's a good question. Right now, we have, I don't think we have actually an answer for that question. We can follow back up in the written responses. We're looking to see what is appropriate for these things right now. So I think that takes a little bit of both modeling and simulation as well as seeing these systems deployed in the real world and getting some real high quality data to understand where do you actually have tipping points when dealing with these types of disturbances so that we can add those into the specifications. Again, realize, right, what's available now is version 1 of the specs. We're looking for people to read through these, give us comments back, and if there's things like, oh, well, we need more detail in this section around phase jumps, that would be an awesome comment to send us back.
Okay. I think I'm hopefully can squeeze in another 2 questions here, Ben. First one, very practical question. Are grid forming inverters already commercially available?
Yes, mostly on energy storage systems. I know that on wind systems and on photovoltaic systems, they are under development. I don't know if they're commercially available, but they are out there. They are under development right now. So for battery energy storage, grid forming inverters are currently commercially available.
Okay, this last one, I'm not quite sure exactly, but it reads, how well does the instantaneous IBR formula go with FERC's November 22 rulings on concerns over reliability gaps associated with IBRs? Instantaneous IBR formula.
Well, yeah, I think what the challenge with the instantaneous IBR level is it's just one point. It's convenient to have a conversation around. It surely doesn't tell you if the system is stable at that point or not. And as I showed on some of those graphs, you can be unstable at 20% inverter-based resources if you put them in the wrong places. So again, it's system dependent. But in general, in terms of rules of thumb and places we've been able to migrate the industry toward, it's this higher level, say 60 plus instantaneous with inverter-based resources. You want to start considering grid forming technologies.
Okay, so we're about at the top of the hour. I think we're going to need to wrap it up. And I want to thank you, Ben, for this really informative presentation to help us get oriented on grid forming specs. And I really look forward to the final results as they evolve. As I mentioned earlier, an email will go out once the video file has been posted. We'll answer the questions we didn't get to, so stay tuned for that, and we'll get them posted as quickly as we can. We appreciate your engagement, and if you'd like to stay engaged, I'd invite you to participate in the next e-cig webinar this Thursday on market design for systems with a high share of renewables with Ben Hobbs of Johns Hopkins University. I'd also invite you to attend the e-cig Spring Technical Workshop in Arizona at the end of March, where we'll have some grid forming sessions. And further information on all of our webinars and events can be found on our website at esig.energy under events, and you're all invited to attend. Information on all the G-PST webinars can also be found at globalpst.org. Ben, I want to thank you again for this very timely webinar, and thank all of you for your interest. We look forward to seeing you again in the near future. And in the meantime, everyone, take care, stay safe, and thanks again for your participation. Bye now.
Thanks, Charlie.